Okay, welcome to video number 6 for PSPICE. What I'm going to do in this video is go through example 512 from the Circuits 1 lecture. This is in the Hulaby and Harvey's Circuits text on page 239. I'll be doing this example for both PSPICE and for multisim. So for PSPICE, I've gone ahead and added the components. The problem asks us to find the voltage across the capacitor given a pulse waveform that lasts for 4 seconds and has an amplitude of 10 during that time. It starts at 0 and ends at 4 seconds with a 25 kilo ohm resistor and a 0.2 millifarad capacitor. So the circuit is shown on page 240 in figure A, and so I went ahead and placed those components down. I'll go ahead and connect them up, and then we'll talk about the pulse waveform, make sure that we connected that correctly. Alright, so for the pulse waveform, there is no delay. It starts at t equals 0. It has a voltage that starts at 0. No time delay, so it starts at t equals 0. Voltage is 10 volts. Now my rise time and fall time I set to be a very small 1 nanosecond. We can't put 0 there. We can't have an instantaneous change. That's about the best we can do. We're talking about a 4-second pulse. A 1 nanosecond rise and 1 nanosecond fall time is practically instantaneous, but also more realistic. I set the period of the pulse to be 20 seconds so that it basically stays 0 from 4 until 20, just to match the figure that they have in the book on page 240 again. So we're going to go ahead and do a transient analysis. So we'll call that simulation or simulation profile. Open up the simulation profile. We're going to be doing a transient analysis, and let's go ahead and run this. We'll just run it for 20 seconds, and our step size can be point. We'll have a lot of points if we do every nanosecond, but let's see if we can do this. Let's just set this up to be about a millisecond. I'll tell you what I'll do. Since our length of time is so long, let's go ahead and set the rise time here to be 1 millisecond and the fall time to be 1 millisecond. We're probably still not going to be able to see any significant delay in the rise and the fall. It'll look pretty instantaneous. Okay, so from there, I'm going to actually go ahead and plot a couple of things. So I'm not going to put any probes on here. When I do that, I like to use my ports. That's one of my favorite ports, and we'll call that port out. We could call it BC, but I like to call it out. That's what we'll be looking at. Let's go ahead and run that, and then we'll pull up our probe window and place some plots on there. A long time to run, but we're finished, and so we can see that our time axis goes from 0 to 20 seconds. There are no errors, and we can go ahead and add our traces. First one I'm going to add is the voltage across the capacitor, which is V out, and we do get exactly what we thought. If you go back to your lecture notes from Circuits 1, you saw that at t equals 4, we found this to be 5.5 volts, and then it decays from there. We can add the input waveform, but I want to go ahead and show you how we can plot the current as well. So let's add a trace, and let's look at the current coming out of V+. It should be hard to see it on that scale because it is very small. let's go ahead and remove that trace and add it again. The current leaving V1, which is the current in the series loop. You can see that it's negative as the capacitor is current is negative, flowing, it should be charging the capacitor and discharging the capacitor. Okay, I went ahead and deleted that trace and start over. I want to show you a couple things here real fast. So we have these different currents here. Now there is just one loop current going through, but it's obvious that which one we choose, we're looking at a direction of current. So what I want to look at here is the current going into the capacitor. See that if I select it, it's showing the current that is leaving the capacitor is negative. Obviously the capacitor is going to be charging up during the cycle with pulses high and then discharging. Okay. So it's telling us the current that's pointing from the capacitor going back into the source. So we can also look at the amount of power being supplied by the capacitor. So the capacitor with current going into its terminal is going to be positive, so it's absorbing power when the voltage is 4 volts or 10 volts applied and the pulse is at 10 volts. And then when the pulse turns off, the capacitor becomes a source and delivers power to the circuit until it discharges to 0. Okay. So again, we can add and look at the voltage across the capacitor. And we can add voltage source. Now one other thing you could do, since the scale of the voltage and the current is so different, we can add a y-axis. Now we have 2 y-axes. Now let's see if we can add a trace. Let's see if we can add our current through R1. Let's delete that axis. Try to add it again. I'm trying to get both plots showing at the same time, both having decent scale. Okay, so there's the current through the resistor showing as 400, starts at 400 microamps and then switches to negative as the current starts to come from the capacitor, and the capacitor is delivering power. Alright, so let's try to add the y-axis first. Oh, it crashed. Okay, so we're back. So I've reopened probe, added a y-axis, and I can select the first, the second y-axis to plot. So I'm going to put current on this axis and voltage on this axis and see if we can get both on the same plot. So let's go ahead and add the current trace, and it looks like IR1 gives me the waveform that I want for current. And now we'll go to the second axis and add the voltage. There we go. So the fuchsia line, or the pink line, showing current into the capacitor as it's charging, and as it's discharging. And we could even add another, see if we can add another axis. And this axis will add the power absorbed by the capacitor, and that's in yellow. Like yellow. Can't see that. So let's turn that one blue. There we go. That's better. Okay, so So now we have current, voltage, and power all showing up on the same plot. Alright, so that concludes the example of how to use PSPICE in the transient analysis to solve the problem. And again, this problem is example 512 from the Circuits 1 textbook.